All right, so today we're going to jump from Chapter 2 to Chapter 3. We're going to talk in Section 3.2. We're bypassing Section 3.1. We're just going to go straight to Section 3.2. Today what we're going to do is we're going to talk a little bit about the polynomial functions of higher degree. Okay, so what are some of the properties that we have of polynomial functions? Some of the terminology. I just want to talk a little bit about a couple of those things, and then we're going to jump right into examples. I'm not going to go through every single facet of these notes. Part of the reason why is I wanted to pretty much summarize what the textbook talks about. This is a pretty long section, actually, if you read through it in the textbook. So my goal was just to try to summarize it as best as I can, just with a couple of examples. So the one thing that I want to, there's really two big things in the notes that I want to talk about. Number one is the term degree. Okay, so if you see that anywhere when you're asked what's the degree of this polynomial, what you're looking at is the highest exponent. Okay, so for example, this right here is a polynomial technically. There's no x term, but if there's no x term in anything, or I should say variable term, x in this case, then in this case it's a degree 0 polynomial. Okay, here this has an x to the first power, which means it's a first degree polynomial. A quadratic equation, which is this one, ax squared plus bx plus c. This guy right here, the highest exponent is 2, which means this is a degree 2 polynomial, or second degree polynomial. Okay, so it's, again, the highest exponent connected to it. We'll talk a little bit about mins and maxes. We've already looked at that briefly. I think there was a couple of instances where we saw that. Again, this is a lot of very specific terminology. That's one of the things in math that you find is that math is a very specific topic. I used to have a friend of mine when I was teaching calculus in graduate school. He was another graduate student, and he would always have a true-false section on his exams. I do not personally like true-false sections, but I kind of understand why he did it. For literally every single exam, he would make 10 true-false questions, and every single one of them would be false every single time. And you're like, what the heck? You know, when you're taking the exam, I'm sure you probably think this, but you're like, man, there's no way that I can possibly have 5 or 6 of the same answer in a row, you know, not to mention 10, right? But he intentionally would do all of them false, and the reason why is because he would take a tiny little section of every single problem or thing that he was asking, whether it was true or false, and he would change just a tiny little bit of it. When you do that, because in math, things have to be very specific and perfect, essentially, and when you're working through things, everything was false. So, again, it is very difficult for things to actually be true in mathematics. It is very easy for them to be false. So that's actually just something that always kind of stuck with me. I thought it was pretty funny. The intermediate value theorem. I'm actually going to come back to this. I want to pose a question to you if you can think about it. I'll pose it right now, and I'll give you the answer here in a little bit. So the way that I like thinking of the intermediate value theorem is kind of like when you grow. You're a little kid. Say you're a little baby. You're just born, and as you get older, you grow. When you get to, I don't know, say 18, 19 years old, you're pretty much going to be at your height. That's going to be the height the rest of your life. I'm just kind of forgetting, like, if you get really old and you start shrinking, which happens, you know. What happened? Okay, so between the age of being born to the age when you reach your max height, the question I have for you to think about: are you at some point between those time periods, every single height possible between the time that you're a baby and the time that you're 18 years old? In other words, if I grow to be 5'10", will I be at some point 4'3"? Exactly 4'3". We'll get back to that in just a few minutes. Even and odd powers, again, this is really just explained by doing a few examples, so we'll go ahead and do that. All right, let's jump into it. Let's look at some problems here. Pull this up. All right, so first thing that we're going to do is we're going to look at some of the behavior on the far left and the far right. So when you have a polynomial like this, you can actually determine what is happening on the far left and far right of each equation based upon the leading term. So you look at the exponent and you look at the leading term to tell what's happening. One trick that you can do is, you can use Wolfram alpha just to plot it to get a good sense as to how these work. But here pretty much is your general rule, okay? So you look at the leading coefficient. Leading coefficient. Here's kind of like my process, okay? So in this case, it's going to be -2, okay? So what you're doing is you're looking at the sign. You want to see if it's negative, okay? So this is negative. Then you look at the exponent, okay, connected to it. So in this case, it's a 3. So this is going to be a 3, okay, which in this case, you're looking to see whether it's even or odd. So 3 is an odd number, okay? So what this is telling us is that when we have a negative coefficient and an odd number for the exponent, the graph is going to be on the far left, coming from above. It's going to be up at the very top, and then down to the far right. So it might look something like this, okay? That might be what the graph looks like. So in this case, when it's negative and odd, it's going to be down. If it's negative and even, let me actually draw all the scenarios so you can see. So in this is kind of like the one example that I just showed you, kind of did it for you. But let me show you all the possible cases, okay? So you've got something that might look like, let's see here, something that might look like this. Say it's like a little parabola looking thing. You can have something that is going to be like that. Okay, and again, these aren't exact. It's just kind of a basic representation of what it will kind of somewhat look like. If we have something that, so in this case, let me just put these properties here. So the leading coefficient, I'm going to call it LC, is going to be, in this case, positive. The leading coefficient's positive. The exponent, or the degree is even. You're going to have this case here, okay? If you have the leading coefficient, I'll do a capital L just to make it consistent. The leading coefficient is positive and the degree is odd. It's going to look like this, okay? So what happens when we flip it around? So the leading coefficient, now we do leading coefficient negative, and the degree is even. We're going to have something that looks like this, like a rainbow. And then if we do leading coefficient negative and the degree is odd, it's going to be like this, okay? So you can kind of see, like, there's 4 different cases that you can run across, and frankly, sometimes, I'll look at it and I'll just kind of forget it. You have your notes in front of you. I encourage you just to take advantage of that. And so always, feel free to plot it too. Use a device if you've got a calculator or Wolfram alpha. So that's just the general kind of rule that we have for those. All right, let's just do one more, 12. P of x. So P of x is our function. We've got 3/4 times x to the 4th minus 5x to the 3rd plus 6x squared minus 3x plus 7. You can kind of notice, actually this is a minus 7. It really doesn't make a difference. Again, when we're looking at the The far left and far right behavior, we're just looking at this guy right here and this guy right there. Okay, so in this case, 3/4, this is positive. So the leading coefficient is positive. The exponent is, or the degree is even, which means that it's going to look something like this, which means far left is going to be up, far right is going to be up also. Okay? So the far left, it's going to be at the top. It's coming from the top. To the far right, it's also going to be coming from the top as well. Okay, so that's 12. All right, finding the relative min and the relative max. How do we go ahead and do that? Well, I'm going to actually show you how to do it on Wolfram Alpha. There are ways to do it as well on a graphing calculator, but I am not going to do that right now. Minus 16. So let's go ahead and switch over to Wolfram Alpha, and I'm going to punch these values in. Pull it up here. All right, so we've got x to the 3. Oops, got to be in here. X to the 3 plus 4x to the 2 minus 4x minus 16. And what we can do is we can actually go ahead and just hit enter. Let's see what happens. Okay, so here's the input. Here's actually the graph that they give you. And they'll actually give you the roots. Don't need to worry about that. Don't need to worry about these things. The local max and the local min, these are actually the things that we want. So you can kind of see, they give you approximate form, or the exact answers, I should say. The approximate form, if you want to put it into like a decimal, you can go and hit approximate form, and it'll actually give you the decimal representation. So the way I read this, from left to right, the max occurs at, this is actually a y value right there, and they give you the x value of where that y value occurs. Same thing down here, the local minimum is going to be a minus 16.901, so that's the y value. The x value is going to be a 0.43. So another way, by the way, the notes, if you read through them, here the term is being used, this actually says local maximum and local minimum. Relative and local kind of mean the same thing in math, so that's just something to be aware of. If you see local or relative kind of swapped out with one another, just know that they are referring to each other. So in this case, when you look back up here, there actually isn't an absolute max or an absolute min. Absolute meaning on the entire function. When you're looking relatively or locally, you're kind of looking in small little pockets. So you can see there's a bit of a hump right here. So that's where that little pocket shows up. That's why there's a relative max at that area. And here there's a relative min at this area because there's a bit of a peaks and valleys. You can kind of think of it like mountains and all kinds of stuff. So yeah, that's basically the idea right there for these kinds of questions. All right, let me switch back, and we'll go through some more examples. Okay. I'm not sure how WebAssign is going to ask you to do those questions. They might say that you have to put them in to the nearest tenth or something like that. I very strongly suspect that they would not ask you to do something exact like Wolfram Alpha did. Wolfram Alpha is probably using a very strange specific formula to get all that stuff that's like way more complicated than and is outside the scope of this class. All right, so let's actually find the real zeros by factoring. There's some behaviors we can look at here. Real zeros by factoring. Okay, so we've got p of x is equal to x cubed minus 6x squared plus 8x. Now, one of the things that you'll notice is that you can factor an x out of every single one of these terms. So this is the same as x times x squared minus 6x plus 8. And we can actually factor this even further. The factors of 8 are going to be, it looks like 4 and 2 in this case are going to produce a 6. Since that is negative, then both 4 and 2 are going to be negative as well. So this is x minus 4, x minus 2. Notice if I multiply the minus 4 and the minus 2, I get positive 8. If I add them together, minus 4 plus a minus 2, that's going to be a minus 6. So that's kind of the factoring right there. So now if we're finding the real zeros, what we're doing is we're actually setting this equal to 0, which means when you use the property by separating them all out, x is equal to 0, x minus 4 equals 0, x minus 2 is equal to 0. Okay? So this one's done. We can move the 4 to the other side. This is going to be x equals 4, and then this guy is going to be x equals 2 right there. So these guys are all the real zeros of that function. All right, let's go ahead and jump to this question. Ah, yes, the intermediate value theorem. Okay, going back to my question that I asked you earlier on. If you're growing between the age of being a baby and being an adult, 18 or 19 years old, will you be at any point, at any specific point, a specific height? Or I should rephrase and say that will you have every single height in between your starting and ending point at some point in your age growth, right? And the answer actually is yes. You do not skip heights. You will always have to be at some moment in time every height between what you started at, I should say, as a baby, and what you will ultimately grow into as an adult. You will be every single height at some point. And actually, that's what the intermediate value theorem states. What it's saying is that there's going to be a point. So let me bring the notes back up here so I can read directly from it so you can see. So if you have a polynomial function where your y values are not the same, and you've got an x value here that's smaller than some other x value, right? Then what happens is your polynomial, your results, your y values will be every value between p of a and p of b within that interval. So in other words, for every single value between, say, like one x value and another x value, you will have every single y value represented if you have a function. It's kind of crazy. Let me actually illustrate how this works. So question 28, they're saying use the intermediate value theorem to verify that the polynomial has a 0 between a and b. In other words, the polynomial crosses the x-axis at some point. Okay? So here's what we're going to do. First, we're going to start with our polynomial. Let me write this out. P of x is going to equal 4x cubed minus x squared minus 6x plus 1. Okay? So P of a, they give us the values of a is equal to 0 and b is equal to 1. Okay? Which means that we need to find p of 0 and p of 1. So p of 0 is literally just substituting 0 in for every x value, minus 0 squared minus 6 times 0 plus 1. This is equal to 1, right? That's 0, that's 0, that's 0, that's 1. So we're left with just that. All right, so P of 0 is equal to 1. P of 1 is equal to 4 times 1 cubed minus 1 squared minus 6 times 1 plus 1. So this is going to be, what, 4 minus 1 is 3, minus 6 is minus 3, plus 1 is minus 2. Okay? So the way that you can think about this, so really the big thing you are looking for in this case, if you're looking to find that this has a real 0 between these two x values, what you want to notice is that there's actually a sign change between this and this. And since one of these is positive, one of these is negative, then using the intermediate value theorem, that means that there must be a real 0 between those two specific points, or between these two x values on the function. So how would I write that out? A lot of times when we're proving stuff, it's good to write everything out. So between the points, a is 0, 1, and 1 minus 2, y changes from positive 1 to negative 2. Therefore, by the intermediate value theorem, which I'm going to call IVT, this function has a 0. Okay? So that's how you would go about getting to that specific point. I feel like I'm a little bright. I don't know if my screen brightened up a bit. Maybe that's a little better for you. If you're having a hard time seeing over that glare, I apologize. All right, let's go ahead and do one more of these so you can kind of see how to do it. Again, we're just taking the a and b values that they supply, that they give to us, and we're substituting them into the equation. And we are really, in this case, just looking for a sign change because we're trying to find or show that there's a 0 between those 2 points, or those two x values. So, question 30. They say that p of x is equal to 2x cubed minus 21x squared minus 2x plus 25. P of 1 is equal to, sorry, I should write these down. A is equal to 1, B is equal to 2, okay? So 2 times 1 cubed minus 21 times 1 squared minus 2 times 1 plus 25. All right, so you can actually go ahead and do all this. This is going to be 2 minus 21, which is minus 19, minus 2, which is a minus 21, plus 25, which is going to equal 4. Okay. P of 2 is equal to 2 times 2 cubed minus 21 times 2 squared minus 2 times 2 plus 25. Okay, so what do we get? I feel like this is going to be a pretty big number. Let's try it. 2 times 2 times 2 times 2 is actually 2 to the 4th, so that's actually going to be 16. Let's just write it out real quick. 2 squared is going to be 4. So 4 times a minus 21 is a minus 84. Then we're going to get a minus 4 here, and then plus 25. Okay? So how do we want to do this? 16 plus 25 is going to be 41. 41 minus 84 is going to be a minus 43. I feel like I did some, no, minus 43 minus 4 is going to be minus 47. Okay, we're good. Minus 47. All right. Mental math, it's awesome. Okay, so here we go. So again, the way we write this out, notice the sign for the y value is different. So this one's positive, this one's negative, which means by the intermediate value theorem, y changes from positive to negative. So we must have a real zero on the function between x is equal to 1 and x is equal to 2. Okay? All right, we're almost there. There's one other application to polynomial functions that you can run across. Some of it deals with the behavior when you actually are looking at factored forms. So that's just the one last thing that we're going to talk about for this one section. And I'm going to show you kind of what this looks like. Question 38. P of x is equal to, in this case, they're saying find the, what are they saying? Determine the x-intercepts of the graph. Find each x-intercept. Use the even and odd powers of x minus c theorem to determine whether the graph crosses the x-axis or intersects but does not cross. Okay, that's saying a lot. Long story short, here's what we're doing. You take a look at the factors and you're looking basically at the exponents, whether they're even or odd. If they're even or odd, they're going to tell you a specific characteristic or attribute of the graph itself. So here's what you get. When you got odd powers, this is again just for factors only. Okay, you can see this is in factored form here. Okay, so when you have odd powers, again for factors, what's going to happen is the graph is going to cross the axis. And when you have even powers, again, it's for factors, same idea. So in this case, there's a 2. It's going to touch, I should say the x-axis, by the way. The x-axis. Camera just shut off. Give me just a second. It's got this 30-minute timer on it, and then it just doesn't like to cooperate with me. So, yeah. Even powers, it'll touch the x-axis but not cross. Okay, and I'm going to show you what this looks like in Wolfram Alpha. So, in this example, what we're going to do is we're actually going to go and do each factor, set it equal to 0. Okay, x minus 6 equal to 0. You do not need to worry about the exponents here. So bear that in mind. So we've got x minus 6 equals 0, x plus 2 is equal to 0, and then we just solve. So x is going to equal minus 2, x is going to equal positive 6. So what happens at each of these specific points with regards to whether it crosses or does it just touch and not cross? And that's where these powers come in. So after you find the specific critical points or the critical values, you're going to look at the exponent that was attached to that factor, and if it's odd, then you know that that is where it crosses the x-axis. So here is where it crosses, and here is where it touches but does not cross. Okay. So let's go to Wolfram Alpha. I want to show you exactly what that looks like. Pull that up here. Just give me 1 second. We still got our old example. All right, so let's go ahead and pump this in. X plus 2, x minus 6 to the second power. Okay, so if I hit enter and I scroll down, you can see exactly what happens, right? Here's the picture of the graph. So right there at x equals 2, or minus 2 I should say, which is the one root, or the 0 that we found, at x equals minus 2 it's going to cross, but down here at x equals positive 6 it touches the axis but it never crosses it. Okay, so that's really what this is talking about. When you look at this graphically, you can actually tell just by looking at it, oh yeah, that makes sense. It's going to cross here at minus 2 because again, the input that I have here, the exponent on the x plus 2 is even. It's a 1. Or I'm sorry, odd. Getting my odds and evens mixed up. X plus 2 raised to the first power has an odd exponent, which means it crosses. An even exponent means that it's going to touch but not cross. So that's how you go ahead and you can actually graphically see how those work. Okay. All right, let me go ahead and switch back. We'll do one more example, something a little bit bigger. All right, so for question 40, same idea. P of x is equal to 2x minus 8 to the first, x minus 7 squared. Now, here's the thing. They will not, when they give you the question, they won't put that to the first power or the first degree in there. I usually just do that just so I can spot it real quick. So just by looking at this and using our knowledge, let's solve these individually. 2x minus 8 is equal to 0. X minus 7 equals 0. 2x is equal to 8. X is equal to 4. X here is going to equal 7. So now we've got a couple of things. So at x is equal to 4, which is right here, because it's an even, or I'm sorry, it's an odd, man, I'm getting my odds and evens mixed up. Because it's an odd number in the exponent up here, it will cross the axis, the x-axis, at x equals 4, and because of the 7 has a 2 on it, it's even, it will touch but not cross. The x-axis. Okay? So that's how you go about doing problems like that. Those ones are pretty straightforward. It's really just looking at the exponents and making sure you find what those roots are, and that's pretty much it. So that's all for section 3.2. If you have any questions, don't hesitate to let me know. Have a good one.